Okay, this is Algebra 2, Lesson 2.1. This is part 2. We're picking up with example number 2, graphing these relations. First one, A, tells you to graph the relation with the ordered pairs given, negative 1, 1, negative 1, 3, 1, 2, and 2, negative 2. So graph each one of those pairs. Negative 1, 1, be at negative 1, 1. That'll be right there. Negative 1, 3 will be there. 1, 2 will be there. And then 2, negative 2 will be there. Okay. If you were to map that out, you'd be able to tell that that's not a function. And you could see it's not a function by looking, this negative 1x value pops up twice. If it ever pops up twice and it doesn't have the same y value, if it's not the exact same point, then it's going to fail something called the vertical line test, which we'll talk about in just a minute. Same thing with graphing this one. 1, negative 2, 2, 1, 3, 2, and negative 2, 2. Just plotting the points. Everybody in here knows how to plot the points. The only mistake anybody ever makes with this is they'll put y before x sometimes. If you ever get confused with that, remember it goes alphabetically. A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Remember that. It always goes alphabetically, X, then Y. On the back, everybody, graph each of these. Just do them real quick. You don't have to go past the number 3 in any direction. In fact, let's do one at a time where we can stop. Do that one. Take 20 seconds. You ain't got to go past 3 in any direction. Remember, the arrows represent the relation. So the first relation, the first one you're going to graph is negative 3, 1. Those are the two that are paired. So at negative 3, positive 1 is there. The next one you're going to do is 2, 3. So at 2, 3, remember, x is first. That's the inputs. Y is second. Those are the outputs, or your domains and ranges, respectively. And 3, negative 2 at 3, negative 2. That's what it should look like. Do this next one. Take 30 seconds. Again, you don't have to go past 3 in any direction. You don't have to be pretty. You don't have to be fancy. Just get it done. Okay, the first one, negative 3, negative 1. Those two to go together. Negative 3, negative 1 will be right there. The next one, negative 1, 1. So at negative 1, positive 1. The next one, 1, 1. So at 1, 1, it'll be right there. And then the last one, 2, negative 1. Will be at 2, negative 1 right there. So that's how it should look. Again, it doesn't have to be pretty. It doesn't have to be exact. Just get it close. We forgot one, in fact. And all that circling I did kind of made me miss it. We forgot this last one right here, everybody. We forgot, notice 1 goes to 3 as well. 1, 3. Because it had 2 arrows leaving it, which we know makes it not a function. Okay, here's your checkpoint. It says identify the domain and range and tell whether the relation is a function. We could do it real quick. We can say this is the domain, this. We can say this is the range right here, the outputs there. Is it a function or not? No, it is not. There's 2 arrows leaving, or there are 2 arrows leaving that first input value, negative 1. Therefore, it's not a function. When it tells you to write the relation as a set of ordered pairs, you'd write it as negative 1, negative 2. You'd write it as negative 1, positive 2, because negative 1 went to both of them. You'd write it as 1, 0, and you'd write it as 3, 0. Those are the 4 ordered pairs that each of the arrows represent. Okay, vertical line test. I mentioned it to you, showed it to you a little while ago. It is a function. The graph or the relation is a function if and only if. In geometry class, y'all saw this phrase, if and only if. You may have seen it abbreviated as if for fa. Y'all remember that? So if you ever see that, don't freak out. If and only if, IFF. No vertical line intersects the graph of the relation at more than one point. When you're looking at graphs such as this, if you took a vertical line test and you drew a bunch of vertical lines, it wouldn't hit it twice. You could do it to anything. If the graph looked like this, for example, there are graphs that look like that. They're not straight linear graphs, but there are. You can see that it fails the vertical line test because anytime it hits one line hits it more than twice, or anytime the graph hits one line more than once is a better way to say it, it fails the vertical line test. So example number 3 is using the vertical line test in real life. It says the graph shows the scores S and time spent T for several students who took a test. Are the scores a function of the time spent studying? So what this is asking, this is a real life question to go along with it. It's saying if students spend more time studying, will they do better on the test? Now, traditional thought behind that is yes, you know that you'll do better if you spend more time studying, but there's always some students that can study for hours and hours, not do so well, and those other jokers that don't have to spend any time studying that'll do well. So that breaks the math behind it. It makes it to where it's not a function. But the reason we could see it's not a function is only because right there, and I know I can't draw a straight line very well, but only because right there, that vertical line gets hit more than once. Okay, if we drew a whole bunch of other vertical lines, none of those would intersect the graph more than once. Each of those only hit it one time apiece. But on that one, it hits it twice, and it only has to do it once to make it not a function. And then all it says is that 60-30 and 60-50, it's hitting it on those 2 points right there, or here on this one vertical line here. Again, just most of the time with the vertical line test, you don't even have to physically draw the lines. You could just mentally draw the lines and see if you run into a point or if you hit the graph more than once. Okay, you don't have to copy this one down, but mentally, everybody do the vertical line test and determine if it is a function. It says the graph shows the ages A and heights H of players on a high school basketball team. Are the heights of the players a function of their ages? Explain why or why not. Just like the example we just looked at, if we do the vertical line test, we can see this first one is going to hit right here. There are more than one instance where a vertical line test is hit twice. But this fails it as a function. Now, as you grow, you guys all started out as babies just like me, and you're turning into adults even as we speak. But as you grow, uh, throughout the ages, you have gotten bigger. You have gotten taller and stuff like that. So we're talking about heights. So again, traditional thought is the older you are, the taller you get. But if you think about this, we all know people who are shorter and people who are taller, and the ages don't match. So if basically mathematically, it's this is trying to say that the older you get, the taller you get, and we all know that that's not absolutely a true statement. So that's the reason why it's not a function. But mathematically, the reason why it's not a function is because it fails the vertical line test. When you graph an equation in 2 variables, it says to graph an equation in 2 variables, follow these steps. First off, construct a table of values. This is a table of values. This. Input, output, x comma y. If you have to put the middle section where you're actually working the expression out each time, put the middle section. Most of the time, you don't have to. Most of us in here good enough with our arithmetic, we don't have to. Step number 2 is to graph enough solutions to recognize a pattern. With a linear equation, it's easy. You can see the straight line. But we'll be dealing with things that are not linear equations in here. So you want to be able to at least recognize the pattern. And then connect the points with a line or a curve. Now, this is if it is something that we can actually graph, if it's something like heights and ages of basketball players, you won't be able to graph that into this. It's just you make something called a linear regression, which is a line of best fit. If you ever hear that term linear regression, it's a line of best fit for all of those because they're not in a straight line or anything you can actually connect the dots with. It would look funny to connect the dots. Now, everything we do in here, when we do all of these tables of values, they'll be horizontal like this. -3, -1, 0, 1, 3, across like that. Notice a second ago when I told you to draw a table of values, I showed you one that was vertical. Most people are more comfortable drawing that vertical one like that. But the first ordered pair, you always want to use numbers that are on the other side of 0, so you have to include numbers that are negative, even though you don't want to. But use numbers that are easy to work in your mind. 0 is the easiest number for everybody to work because when you multiply by it or you divide the number 0 or anything like that, you can get rid of that number. You can cancel it out. 1 is another number that's easy to work. -1's pretty easy too, as long as you don't lose the negative. Okay, and then sometimes you use 2 and -2 because you need one more point on both sides. So don't be scared to use 2. In this case, that we use 3 and -3. But if we plug in place of x, if we plug in -3, -3 minus 1 just gives us -4. So we have an ordered pair right here, -3, -4. Again, if we plug in the next value of x, -1, now -1 minus 1 is -2. We have our second ordered pair we can graph. If we plug in 0, our next one, 0 minus 1 is -1. There's our third ordered pair. If we plug in another one, 1 minus 1 gives us 0. And finally, if we plug in the last x value, 3, 3 minus 1 is 2. Now we got 5 points we can graph. We can graph -3, -4, which would be here, -3, -4. We can graph -1, -2 here. We can graph 0, -1 there. We can graph 1, 0 there. And then finally, we can graph 3, 2 there. And you can see the straight line pattern right there. It says plot the points. Notice the 5 points are in a line, and then draw a line through the points. Very simple. And again, this was the first way you learned how to graph a linear equation. We're going through this to remind you how to do this. That way when you see curved lines, you don't freak out. On the back, okay, on the back, everybody, graph this one with a table of values. Don't graph it as mx plus b. I know you know how to do that. Graph it with a table of values and use easy numbers. Use numbers -2, -1, 0, 1, and 2. Use those just to remind you how to do it. I know. Now let's work through this quick. You should mentally be able to work through these quick. Don't lose the fact that there is a negative in front of the x though. So it's -2, which makes it +2 minus 1, which is 1. So if you got -1 for right there, you might have to go back and change it, or you're definitely going to have to go back and change it. -1 again, or the negative x, makes it -1, which is 1 minus 1, which is 0. It doesn't matter if the next one 0 is positive or negative, it's still 0. 0 minus 1 is -1. Now you got negative x, which makes this next one negative 1 minus 1 is negative 2. And then you have negative x again. Negative 2 minus 1 is negative 3. So then just graph each one of those. We don't have to go past 3 in any direction. Notice there's no value that's bigger than the number 3. So if we just go 1, 2, 3, we can fit our graph we need. And if we graph it, negative 2, 1 will be here. Negative 1, 0 will be there. 0, negative 1 will be there. 1, negative 2 will be there. And then 2, negative 3 will be there. And the only reason mine isn't perfectly in a straight line is just because there's a little variance on how much my lines are spaced apart and stuff like that. Once you have those points, though, you connect them just like Pee Wee Herman. You connect the dots. Okay. And again, that's the first way you learned how to graph an equation, just like that. Number 2 tells you to use the graph to determine if the plotted points represent a function. Okay. So the vertical line test, does this one pass it or does this one fail it? It passes it. Each one of those points, if you drew a line vertically through it, would not hit another point. So number 2 is a function. That's all that says there. It is a function. Graphing this function, again, I know that y'all know mx plus b. I know you can start at 1 and you can go up 2 into the right 1. That's the fast way we learned how to do it. But the way we just talked about how to graph it, we use an input and an output table. So we use negative 2, negative 1, 0, 1, and 2. Remember, you can use any numbers you want. Those are the easiest numbers, trust me. Negative 2 times positive 2 is negative 4. Minus 1 is, plus 1 is negative 3. Negative 1 times 2 is negative 2 plus 1, which is negative 1. 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus 1 is 3. And 2 times 2 is 4 plus 1 is 5. So when we graph this equation, it'll look just like this. We got to go up to number 5, but we only got to go on this one. 1, 2, 3, 4, 5. The rest of them, we can just go a few out. We don't have to go any further. So negative 2, negative 3 is first. So at negative 2, negative 3, that's your first point. Negative 1, negative 1 is your second point. 0, 1 is your third point. 1, 3 is your fourth point. And 2, 5 is your last point. You can see the straight line. Again, I know I can't draw a straight line through it, but that's where it would be if I could, right through those points. Example number 5 is evaluating function. It says to evaluate when x is equal to 2. Remember, read this. Don't read this as fx. Don't read this as fx, that thingy. Don't say nothing stupid like that. Make yourself sound stupid. Read it as f of x. So f of x is equal to negative 3x plus 4. F of x equals negative 3x plus 4. In place of x, you're going to plug in the number 2. Notice right here, in place of x, we plugged in 2. And in place of here, we plugged in 2. So now you're going to read this f of 2. F of 2 equals negative 3 times 2 plus 4. Now, the mistake I see students making with this is they think they have to do something with this. You do not have to do anything to manipulate that side. You can leave that F right next to that 2, not do anything with it. You're only working the right side. You're only simplifying the right side. So work order of operations. Negative 3 times 2 is negative 6. And then negative 6 plus 4 is negative 2. It just did both steps in one for you. B says f of x equals x squared minus 4x minus 1. Again, in place of each one of those x's, this one, and this one, you're going to plug in the number 2, and that's what's going on there. So now f of 2 equals 2 squared minus 4 times 2 minus 1. Order of operations tells us to do 2 squared first and get 4. And then do negative 4 times 2 and get negative 8. So 4 minus 8 is negative 4. Minus 1 is going to be negative 5. And again, it just jammed all of those steps together because you should be able to work those steps. If you need to, between this line and this line, use this space if you need to show your steps to where you don't lose it. That's perfectly fine. That's what that negative space on the side's for. On the back, decide whether this function is linear, and then evaluate when x is equal to 3. Take about a minute on that one. Okay, a little shorter than a minute. I heard somebody right away when I said, is it linear or not, say no. You can look at this right away and determine it is not a straight line. It is not a linear equation because of that exponent right there. That makes it a parabola. That's going to give us a curved line or something that looks like a great big U when we graph it. Okay, then it says to evaluate the function x equals 3. If it were linear, it would be x to the first power. So we have f of x equals x squared plus 4x minus 1. In place of each of these x's, we're going to plug in that number 3, or we're going to sub it in. So now f of 3 equals 3 squared plus 4 times 3 minus 1. And again, if this makes a difference, which it doesn't here, treat it as if it's in parentheses. Order of operations tells us to do 3 squared, which is 9, plus 4 times 3 is 12, minus 1 if you have to do that. 9 plus 12 is 21, minus 1 is 20. So the function of 3, or f of 3, is 20 for that one. Do the same thing for this next one. Determine if it's linear, and then evaluate it when x equals 3. Again, you don't read this as gx, you read it as g of x. Okay, when you look at this one, I'm cutting it a little short, but it shouldn't have taken you very long. G of x equals negative 3x plus 1. This x is written to the first power. That makes it a linear equation. So decide whether the function is linear. Yes, it is. So the next part says to determine or to evaluate it when x is equal to 3. So g of x is now going to become g of 3 equals negative 3 times 3 plus 4. So negative 3 times 3 is negative 9 plus 4. So g of 3 is negative 5. Again, read it that way. Don't read it as g, that thingy 3. Don't say anything foolish like that. Then your checkpoint says evaluate the functions where x equals negative 1. F of x equals 3x squared plus 1. F of negative 1 equals 3 times negative 1 squared plus 2. Square negative 1, that gives you 1. 3 times 1 is 3, and 3 plus 2 is 5. So f of negative 1 is 5. The other one, f of x equals negative x plus 9, when x is negative 1 still. So f of negative 1 equals negative negative 1. Don't lose that one. It's easy to lose that negative in front of it. So that means negative negative, which is a positive 1. So f of negative 1, 1 plus 9 is 10 for that one. F of negative 1 is 10.